Hey guys, it is Friday, April 17th, and on today's kitchen table chemistry, we're still going to be looking at the ideal gas law. In today's look at the ideal gas law, we're going to emphasize these two here, PM equals DRT, where we're going to talk about density, and then PV equals small m RT over large M, where we're going to be looking at the mass of a sample. In both of these cases, we're going to be using this large M, which is the formula weight of the sample. So the identity of the gas is going to come into play. Now I'm going to try to illustrate this to you by using two examples here. The first one here, what is the density of nitrogen dioxide, NO2, at 110 kilopascals and 35 degrees Celsius? So we're given pressure here at 110 kilopascals, which means we're going to use the large value for R, 8.31, which is liters times kilopascals over moles times Kelvin. T is 35 degrees Celsius, which is then added to and becomes 308 Kelvin. M, because this is NO2, its formula mass is going to be 46 grams per mole. And then D is the unknown. The density of the gas is the X that we're going to try to find. So if we pile everything in here, 110 kilopascals times 46 grams per mole is equal to density times the R value, 8.31 liters times kilopascals over moles times Kelvin, times the T value of 308 Kelvin. I simply rearrange and solve for D, and if I do this, I get 1.98. All the units are going to cancel out except for grams, which is going to come from up here, per liters, which is going to come from over here. So it's going to be 1.98 grams per liter, and that is the density of this sample. Most gas densities will be in and around 1 to 2, maybe 3 grams per liter. They don't weigh much more than that. Okay, that's how we use PM is equal to DRT. In this example here, we're going to use the third one there, which is PV is equal to small m RT over large M. So we're going to have a bit more flying around in this one. Now the pressure here is 2.0 atmospheres. And with that pressure, then I'm going to use the smaller value for our 0.0821 liters times atmospheres over moles times Kelvin. The temperature here is 298 Kelvin. The volume is 38 liters. Large M, because this is N2, large M is going to equal 28 grams per mole. And small m is what is being asked for here. It's asking for the mass of the nitrogen gas here, and that is the X that we're going to try and find. So when we put everything else in to find this mass, I have the pressure of 2.00 atmospheres times the volume of 38 liters is equal to small m, which I don't know, times R, which is 0.0821 liters times atmospheres over moles times Kelvin, times T, which is the 298 Kelvin. And that's all going to be divided now by M, which is 28 grams per mole. So if you think about it without the units on, what it really is here is 2.00 times 38 is equal to M times 0.0821 times 298. Don't ask me why I started to write Kelvin, just always do, over the 28. So it's not that bad. We just simply multiply both sides by 28, divide both sides by 0.0821 times 298, and I get a small m value here when I solve this of my sample size was 87 grams, 2 sig figs, 87 grams, and that is of the nitrogen. And again, if you do this algebraically, you guys are so strong algebraically, I have no doubt you can come up with the right answer. And that's how you solve for small m, and that it's simply a matter of shifting things around algebraically. Now, you may also notice that you could solve this different ways. There's about 3 different ways you could approach this problem at this point, and I would not be disappointed no matter which way you chose if you can come up with the right answer. All right, that is all for today. I attached a few practice problems to do over the weekend, and I hope you're doing okay. We will look at a quiz on this stuff in the early part of next week, and that's about all for right now. Hope you're doing well. All right, take care. Bye.